Morning, am I audible to you guys? Okay, beta. Okay, so yesterday we mainly saw the Minimax algorithm. Now, Minimax algorithm has some problems like if the search space is too big, we have to look into each of this node at a time, and it is going to take a long time. Okay, so wait, let me share my screen. Okay, I hope you can see my screen. Alpha, beta, pruning. So the problem with your Minimax search was that the number of game states it has to examine is like exponential in the number of moves. But we cannot eliminate that exponent, but we can efficiently cut off into half. So it is possible that we can compute the correct minimax decision without looking at every node in the game tree. Therefore, we just took the idea of pruning. Normal prune means what? We just cut off some of the branches, right? So same thing we can utilize in case of Minimax algorithm. So that special type of algorithm is known as your alpha beta pruning. So it is applied to your Minimax standard game tree, then it returns the same moves as Minimax would, but prunes away branches that cannot possibly influence the final decision. So for Minimax algorithm, we have a particular algorithm to follow. Okay. In alpha beta pruning, we basically have two parameters. One is alpha. You can just define it as alpha. Alpha means the best, that will be your highest value. Best choice for your max. Okay. Best choice we have found so far at any point along the path of max. Okay, max means maximizer. So the initial value will be of alpha is minus infinity. Okay, so initial value of alpha will be your minus infinity, and it mainly the choice for your max. Max means the one who will start the game, or you can say the maximizer that will try to maximize the value. Next parameter is the beta. So this is also the best value but it will be your lowest value. Our choice, we have found so far at any point along the path of mean. Okay, so the initial value for beta is your positive infinity or plus infinity. Okay, so you can say alpha beta pruning is just a modified version of Minimax algorithm. It is an optimization technique for your Minimax algorithm. Okay, it will just eliminate the exponent part and will cut the whole tree into half. Okay, so alpha beta pruning will just be like your Minimax algorithm. Everything will be same, just that it might remove some of the leaves, or it can also remove a whole part as well. Okay, so there are certain conditions for alpha beta pruning, or you can say there is a particular algorithm. So let's see what's the algorithm for alpha beta pruning. So this is basically your Minimax algorithm. Alpha, beta. Okay. So we will have a max value for max, and we will have a mean value for the mean layer. So for max value, we can write max value. S is the state for which you want to find a value, minimax value, and alpha and beta. These are the three parameters. Okay. Then if terminal is the state S, then it will returns utility for that state, right? For the terminal nodes or states, we have just the utility values. So now we just say that initial value of the node is minus infinity. Okay. For current state C, in next state S, V dash, the value of your current node will be mean value of the current state, alpha and beta. Okay. If V dash is greater than V, then V will be V dash. Okay. Now, if V dash is greater than beta, then it will return V. Okay. Now, if V dash is equal to alpha, then alpha will be your V dash. Okay. Then just return V. Okay. This is for your max value. Now we also need to find the mean value, correct? So for mean, it's almost same. Just the condition is little bit different. Mean value will take same as state and alpha and beta. Same if terminal S state is your terminal state, then return utility of that particular state. Then we initialize v equal to positive infinity. Okay, so for current state C in next states S v dash equal to max value of C, alpha and beta. Now if v dash less than v, then v equal to v dash. Okay, if v dash less than equal to alpha, return v. Okay, and if v dash less than beta, beta equal to v dash. Okay, and return v. So this is the minimax with alpha beta pruning algorithm. Okay, so obviously algorithm looks quite tricky here, but the few things you need to remember. Okay, it will be easier for you how we can prune a part. Okay, just see this algorithm for a while. Just main point to remember is that alpha means your max value, beta means your mean value. And the condition to prune a part of the tree is when alpha is greater than equal to beta. This is the main condition to decide whether you want to go for a particular branch or you want to prune. The moment alpha is greater than equal to beta, you will just prune away that part of the tree. So your max player will only update the value of alpha and min player will only update the value of beta. So while backtracking the tree, it's a DFS, right? We will first go to the innermost the terminal, then we backtrack again. So while backtracking the tree, the node values will be passed to the upper node instead of the values of alpha and beta. So we will only pass the alpha beta value to the child node. So whenever we will get some value of the node, the alpha beta values will be updated. Okay, so you can just remember like already alpha for max, beta for min. So while backtracking node value, upper node instead of alpha and beta. Okay, then we will only pass the alpha and beta value to the child node. Okay, these are the main points to remember. Okay, we will see the example. It will be much easier to understand. Okay, so let's first see a simple minimax algorithm. Then we will see how alpha beta pruning works. Okay, so this is your algorithm. Suppose I'm just going max, then mean, then again means term. You can just also just write any names here. Just remember the first term will be for max, then will be for mean and all. Okay, so third term is again for max, max, again for max, max. Okay, so next we will have just terminal values 2 and 8, 9 and 3, 2 and minus 2, 9 and minus 1. So these are our terminal values. Okay, so let's just see normal alpha beta, not alpha beta, normal minimax algorithm. So max main work is to maximize the value, and min will select the minimize the value for itself. Okay, so first we will start from here. At this moment we don't know the value, you can just say it's minus infinity. Okay, for v you can just say it's plus infinity, values we don't know. Okay, minus infinity. So first I'll come to this part, right? So I can update the value that v equal to 4 now. Okay, so after this I'll come to this part. Now I have another child for this node, which is 8. So out of 4 and 8, which one is the maximum value? 8, and it's a max. So I will update the value here and it will be 8 now. Okay, this is the value for this particular node. It's a max. Okay, then this value will be passed here to this min. Okay, for the time being I can just say mean value is 8. Okay, now from here I have another branch, right? So I'll come to here. Okay, at this point initially it's just minus infinity, you can say. So here first I saw 9. Okay, so I'll update the value 9, because if you compare which is the greater between infinity and 9, then again 9 will get the highest point. Okay, 9. So next I have another node is 3. So from 9 and 3, 9 is the max, so it will not be updated. V will be just 9. So again I'll pass this value to this node. Okay, since it's a mean node and you can see the value is right now is 8, and it will just select the minimum value, correct? So out of 8 and 9, obviously it will select just 8, which is the mean value. So this value is already 8, so it is not going to update this value. Okay, after that it will pass this value to the root node. Now it will update the value as 8. Okay, so now this value will not come down here. We will send up the node value. We can only uh, pass the value of alpha beta pruning, but here this is just simple minimax algorithm. Okay, so initially we don't know the node value for this node. Similarly, don't know the value of this node, and for this node also don't know the value. Okay, so from here we will come to this point. Okay, for this max, first I got 2. So I can update the value of the node as 2. Next, I got this child. Now it's the value is minus 2. So from 2 and minus 2, which one is the maximum number? 2. Correct. So value is already 2. So I'm not going to update it. Okay, then this value will be passed here. So now I can update it here as 2. Okay, so node value is here 2. So now I am coming to this part. Okay, initial I don't know. So first I am getting 9. So value I can update here is 9. Correct. Next I found another child which is -1. So from 9 and -1, 9 is the highest. So I am not going to update it because it's already 9. Okay, so this is done. The value for this particular node is 9. Okay, so I will just pass this value here. Now from 2 and 9, which one is the lowest? Because it's a mean, it's 2, right? But the value is already 2. So I'm not going to update this value because it's already 2. Now the node value here is 8 and here node value is 2. Now my root node is max, correct? So from 8 and 2, which one is the max? 8, correct? So but the value is already 8, so I'm not going to update it. Okay, so our main ideal part will be this portion, right? This is our part, optimized part for the max. Okay, this is your normal Minimax algorithm. Is this part fine for everyone? Okay, Minimax algorithm clear. Now we will see how we can use alpha beta pruning here. Okay, okay, I'm going to draw the same tree here. Just drawing the same value. Okay, max min min max Now we have terminal values. Okay, so this is the same tree. We will now see how we can use alpha beta pruning to get the optimized value without checking, looking into our whole tree. Okay, so as you can see in this algorithm, see your algorithm can be different one, right? In books, you might get slightly different one, but the basic idea is same. Okay, so I will just follow this one. Okay, it's a bit easier to remember. So here I'm going to need to maintain three parameters. One, the state, or you can say V, then alpha and beta. So V will be your node value and alpha beta value will be just the value we are going to use. So initially I can say V is something we don't know. Maybe you can just initialize with minus alpha, doesn't matter. Alpha and beta. Okay, these values we don't know yet. But as I say, alpha initial value is minus infinity, and for beta it is plus infinity. Okay, so same value we will pass down here. Right now for this one, node value we don't know, alpha equal to minus infinity, beta equal to alpha. So same thing we will pass down here. For this node also, beta will node value we don't know yet, alpha equal to minus infinity, beta equal to infinity. Okay, so we are at this node first. Okay, so now you see we got one value here, 4. So I can update that node value is 4. Okay, so now since it's a max value, what I can say, I can update this alpha value and put it 4. Okay, remember alpha is for max and beta is for min. Okay, so when you will pass the values, then only the alpha beta values will be changed. Okay, so initially the node is 4, so I'm updating the value. Node value is 4 and the alpha will be 4 now. Okay, now I have another child, the value is 8. So from 4 and 8, 8 is max, so I'm going to update it as 8 now. Okay, so node value is 8 now, and we will also update the value of 4, 8. Okay, that means now at this point node value is 8 and also your alpha value is 8. Okay, so finally node value is 8 and also alpha value is 8. Okay, this is max. Okay, so same value I'm going to pass it here. Okay, so when you pass this value, the node value will be passed, that's correct, but here the only update will be in for beta. Why? Because it's a mean node. So I'm going to update this beta as 8. Okay, so when you will pass, you just remember whether it's a max node or min node. If it is a max node, alpha node will be changed according to the node value. If it is a min node, beta value will be changed according to the node value. Okay, so right now only beta will be changed. Now beta is 8. Okay, now I'll pass it here. For this node, I don't know the value yet. Alpha equal to same minus infinity, and beta value will be passed here. Okay, we can pass alpha beta value to the child node. Remember, this is the condition. Only pass alpha beta values to the child node. Okay, and node values will be passed to upper nodes instead of alpha and beta. Here we are not passing the beta value, but we are only updating the value. Okay, so for this node, V is still unknown, alpha is minus infinity or we don't know the value yet, and beta is equal to 8. Okay, now for this node I have a value 9. Okay, so I'll update the value as 9. Okay, so if I update this value as 9, that means I will also update the value of alpha, which is 9. Okay, so for this moment node value is 9, alpha value is 9. Now see, it's satisfying our condition alpha is greater than equal to beta, because beta is 8 and alpha equal to 9. Correct? That means we are going to simply prune this part. We will not check this part at all, because here alpha is greater than beta. Okay, up to this part, is it clear? Why we pruned it?
Hello, ma'am.
Are you saying no?
No, ma'am. Ma'am, I have one question.
Yes.
Ma'am, I didn't understand this condition. This node's value will be passed to upper node instead of alpha and beta.
This is the condition for your alpha beta pruning algorithm. It's not something I'm making. This is just the condition you have to follow. Okay. So node value will be passed to the upper nodes, but you can only pass alpha beta value to the child node. So initially the root node was just everything is just initial values. We don't know the value for root node. Alpha and beta is just initialized to minus infinity and past infinity. Okay, the same thing, it's a DFS. We will come to the left side of the subtree. So in this node, we are just passing the same value. But see, you can see alpha, beta, we are not exactly passing just initial values. They are just minus infinity and plus infinity. So initially everything is just infinity, infinity, infinity. So the moment we reach here, now we have terminal nodes. So for terminal nodes, we are updating the value of node first. We got a value for max, right? So you can check here. The value first we updated was 4. Okay, so first initially it was 4. Initially it was infinite or something, it was 4. Then we check second node, value was 8. So out of 4 and 8, max was 8 because it's a max. So we updated the node value as 8. Okay, so similarly same thing we will do for alpha also, because alpha is only for the max. Alpha is checking the value of max. So for a max node, if you are updating a value of the node, then same value will be updated in case of alpha also. And beta remains same because it's just a max node. So this value I am passing up there. Okay, so when you pass it, the node value will be passed. So initially here v was just infinity, so you are updating the value, you are passing the value of this node, and this node become 8, just like we did for the minimax. It's just same, completely same. Minimax value, the passing of node value is exactly the same like your minimax, just that only difference is the alpha and beta value. Okay, so here alpha will not be updated because it's a mean node. So we will update only the beta value according to the node. So beta value is updated as 8 here. Okay. So alpha remains same here. So this same value we will pass down to the max. Here initially we don't know the v. Node value wasn't passed here. Node value was just empty initially. I just pass value of alpha, which is just minus infinity initially, and beta was 8 because I only pass the value of alpha and beta. Okay, beta is 8 here. Now I got this number 9. Okay, so I updated the value of the node as 9. So since it's a max, I will also update the value for alpha. So it becomes 9. Okay. The value of beta was 8 here, right? So it is satisfying condition. When alpha will be greater than equal to beta, we are going to prune this part. Since here alpha is greater than beta, I am pruning the value. Okay. So I'm not going to check this part. Now I will pass the same value up here. Okay, now v value is 9 here and v value is 8 here, and it is a mean one. That means what? It will only select the minimum value, and the minimum value is 8 here. So it is not going to update the node value because it's already the minimum one. Okay, so here I will again pass the same thing here. That means I will update the value 8. Okay, now node value here is 8. So since it was updated here, the max value, the alpha value will be updated. Okay, now alpha value will be 8. Why? Because it's a max node, right? Whenever you updated the value, if it's a max node, alpha node will be updated. If it's a mean node, beta node will be updated. Okay, so alpha becomes here 8 here. Now you are coming down to the other part. Okay, for this node I don't know the value yet, correct? So I'm just passing the value of alpha and beta. So alpha value was 8, beta was just infinity. Okay, so from here I'm coming down to this node. For this node again I don't know the v value, alpha and beta. Okay, alpha value was 8 here and beta value is still infinity. Okay, now here I'm getting the value 2, so I can update the value 2. Okay, I'm updating the value of this node 2. but here alpha value is 8, correct? I'm not going to update the alpha value here. Why? Because main purpose is to get the maximum value, correct? So I'm not going to update this alpha value because it's already in 8, which is the max value. I'm only updating the node value here. Okay. So now I will pass down this value to your this node. Now node value will become what? 2, correct? So node value will become 2 here. Now since it's a mean node, I will update the value for beta. Okay, so beta will become 2. So since again it's satisfying the condition alpha greater than equal to beta. So I'm going to prune down this whole part. I'm not going to check this part at all because at this node 8 is greater than alpha is greater than beta value. Okay. So this same value will be updated here. So node value for this node is 2 and it was 8 and now it's a max value. So node value here is already 8 and just now I just got a value 2. So I'm not going to update it at all. So this one will remain same. So our optimized way is still the same, 8, 8 and 8. Okay. So the minimax, the node updation rule is just same, just that we have extra alpha and beta value here. So here I just explored each of the nodes and here based on this condition, I'm just pruning away some of the parts. Is it clear how it works? I'm not checking the values for here at all because at this point I would have just come down here, right? But at this point alpha is greater than beta. So I'll just prune down in this part. I'm not going to come here because here it's a max node. Max is 2 and here I'm getting min 2. So if I go down this path, the upper bound would be like 2. No matter what I do, it will be just below 2, right? So here I'm already getting 8 and next value is just the max of 8. So I'm not just going to go down at this part. Is this clear? See, node update process is just same. Okay, Jahid, yes. Arindam, yes. Okay, you can check another one if you want. Suppose I have just take similar this max min max max. Okay, terminal values you can say 2, 3, 5, 9, 0, 1, 7 and 5. Okay, you can try this out in your own. So can you do this? Can you tell me the values here? Initially, everything will be just infinity, alpha minus infinity, beta, infinity. Same will be here as well. Don't know the value of b, alpha, and beta. Plus infinity minus infinity. Okay. Okay, this meeting is going to end in 5 minutes. So this is you can take as your homework. Okay. So from here, you can see that alpha beta pruning is dependent on the ordering. Okay, so effectiveness of your alpha beta pruning is highly dependent on the order in which each node is examined. Correct? If the max value will be like, okay, for this case, if I would have just get 3 first, then 9, that maybe this portion would be pruned, right? So it basically depends on the order. Okay, so move order is very important aspect your alpha beta pruning. So it can be of two types. One is like worst ordering. So in some cases, alpha beta pruning algorithm does not prune any one of the leaves of the tree, and it just works exactly like Minimax algorithm when all the terminal nodes are in the worst ordering. Okay, and in that case also alpha beta pruning is going to consume more time because it just like it will be the leftmost. Yes, yes, it will be the leftmost for here. So this is like your homework. You guys can do it and show me in next class. Okay, so I'm just telling the two conditions. One is your worst ordering. For worst ordering, it will be just like your minimax, and one is ideal ordering. So ideal ordering will occur when lots of pruning happens in the tree, and the best move occur in the left side of the tree. Okay, best move will be in the left side. Okay, so we can just apply our normal DFS, and it just first search left of the tree, and we can just go twice, and we can just minimize the whole timing thing. Okay, so in ideal ordering, it will everything will be in the leftmost part. Okay, and worst ordering, it will be just like minimax, maybe none of the leaves are going to wound. Okay, so to find the good ordering, we have to make sure that best moves from the shallowest node. Okay, so an order of the node tree should be like best node should be checked first. Okay, it's mainly dependent on the ordering. So this is your homework. If you cannot do, I can show it in the next class. Okay, we will just discussing this one in next class in case you won't be able to do. But the whole process is clear to you guys, right? How we can prove. Just remember the condition is when alpha is greater than beta, we will prune away that part. Okay, okay everyone. So I'm just stop sharing. Just switch on your videos for a while. It's going to end anyway. Right. Okay. Okay, I hope everyone just got the idea of alpha beta pruning. Rupa may man haisa. Diken tafazil baki asa. Dike on tipya kaga. Okay, just taking your attendance. Okay, thank you all. See you in next class.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Thank you.